Okay, so good morning, everyone.
Morning, ma'am.
Yeah, so it's nice to meet all of you again. I hope you've had a refreshing break. Yeah, so this break is, I think, crucial for everyone to stay focused. Okay, so I did release the assignment last week because I think some of you felt that it's useful to look at it early on so that you have time to go over the questions. So some of the portions I'll be doing it this week, like things like LP duality and stuff. Okay, so so let's begin. So we were looking at linear programs. Okay, and we looked at one method to solve linear programs, that was the simplex procedure. Okay, so there was this question that Rajneesh had towards the end of last class. I mean, it's about this polytope, like whether the region, the feasible region to a linear program is always convex. Okay, so in particular, the question he had was, in this figure, the parts in red, whether that's not whether that won't come as a feasible region to a linear program. So the answer to this is no. It's never going to be that. This the red part. I hope the screen is visible. Right? Is it visible?
Yes, ma'am.
Yes. Okay. So this part in red, this A, then this middle vertex, then C, D, E. So this part, the feasible region to a linear program can never be this, because if you remember, it's always an intersection of half spaces. Okay. So one side of the hyperplane. So for example, this H1, if you take this side to below the H1 plane, so immediately it's going to rule out the part above it, right? So this part which is causing the non-convexity, that is going to get ruled out. Okay, so in that manner you can see that always you're going to have a convex region as a feasible part of an LP, feasible region to a linear program. Now this, I felt that I wanted to clarify one thing. So sometimes in practice you might end up encountering these kind of regions. Okay, I mean, of course it's not a linear program. So your some optimization problem that you want to formulate, if it comes out like this, now provided your objective is linear, you can always take the convex hull of this region. So that is this AC and ACDE. So okay, so if you even complete this non-convex part, so that it becomes convex. So taking the convex hull of this region, if you take, if you remember, like we saw in one of the earlier classes that optimizing a linear form over the convex hull is going to give you the same objective as optimizing the original set itself over the original set itself. So that's one useful thing which you might encounter at some point in future, like when you have non-convex regions. But provided your objective function is linear, you can try to optimize instead over the convex hull, so you don't lose out anything. Okay, so that's one thing I wanted to clarify. Right. So so now coming to the simplex method. So that's where we were, and we finished this method. So I hope you've got some practice in trying this out, and even the assignment has some questions on it. Uh, so. Uh, so this is one of the earliest methods, the simplex method. Now, for linear programs, there are other methods too. Okay, so the thing about the simplex method is that it makes use of the linear algebra concepts, the underlying linear algebra that's there. It tries to make use of it extensively in order to solve an optimization problem. So that's the thing I found. It's quite fascinating about the simplex. So I don't know. You might be wondering, like, where will we use this, or are we going to use this ever? So perhaps you may not use it in this form, like like implementing a simplex method. So that may not happen because there are more efficient methods now. But all of these algorithms, it's the ideas that come in moving from one feasible point to the other. So based on these ideas that come in simplex, there are different algorithms, and so that is a useful idea to take away from the simplex. Okay, and of course, what we are going to see now is this notion of duality. So that also has some roots in the simplex method. Okay, so that is also one thing to note. Okay, so when we started off with linear programs, I think there was this question of, we include these surplus variables between the slack and the surplus variables. So why do we need two things? Okay, so the reason is, the way it's defined, has its roots again in the simplex. Usually in the simplex method, you try to keep the b values, the right hand side of the linear program. Okay, so you try to keep this as a positive value. Like you would have seen, like based on, you're trying to keep the x's as feasible because we are working in the standard form and you want the x's to be greater than zero always. And if you remember the way we went about the simplex method, at each step you're trying to ensure that x's are greater than zero. And it's some operations on the right hand side that you keep doing to ensure this continues to stay. So it's for that reason that like you have this notion of surplus also, so that the right hand side is always kept positive. Okay, so I hope this point must have gotten a little clear after the simplex method was discussed. Okay, so yeah. So now, so what we saw like in the end of last class is it was just a summary that we started seeing about the matrix form of the simplex method. So where, if you recall that we had basic variables and we had non-basic variables. So the cost function, you can write it as, these two parts. If you have a basis identified, you can write it in this way. So the CB refers to the costs for the basic variables and CN refers to the cost or the objective coefficients for non-basic variables. And again, the AX equals B. Okay, so that was the original problem we had was minimize C transpose X, X equals B, X greater than or equal to 0. Okay, this was the linear program. And this A, you could write it in this way as a decomposition into B and D. Okay, and the basic feasible solution was always XB and 0, where Xns was 0. So now you could write XB using this. You could just write it as B inverse B minus B inverse D times Xn. So the thing was B was invertible because it's a basis for Rm. Okay, and so basically what you had was these kind of operations. So if you try to write the objective in terms of the for this basic feasible solution, what you're going to get is something of this form. Okay, you can just work out the algebra. So now there is this dependence on these xn. Okay, so of course the xn is 0 for this basic feasible solution, but these are what is called the relative cost vectors. Okay, and this is what you try to you use this as a criterion for deciding what's the next basic variable to enter. Okay, so these are the relative cost vector, or it's also called reduced cost coefficients. Now these have some connections with what is called the dual form of a linear program. Okay, so that's what we will do today. Okay, so the dual is usually defined for any constrained optimization problem. Okay, and so it's a general form, but I thought like it's useful to see duality in the linear programming context first, because linear programs are, now we know that those are the simplest form of constrained optimization problems. Okay, with convex regions, exactly linear objective and convex regions. Okay, so let's see duality, what it means in the context of LPs. Okay, so now the thing I just want to take this example here. Okay, so there's this optimization problem in two variables, minimizing 2x1 plus 3x2 subject to these constraints. Okay, so you can derive an other linear program out of this. Okay, it's a related linear program, and that's what a dual is. Okay, so the idea is to, can you construct a lower bound for this problem? Okay, so this is an optimization problem. There's an optimal objective. Can you construct another optimization problem, the optimum of which will serve as a lower bound, okay, for this problem? So to do that, one thing to start off with that, what you could do is, suppose I give you, let's just take an example again. So suppose I multiply these two inequalities with 0.1, okay, some number like this. Okay, so what am I going to get? Let's just write the U form, like, so you'll get what, 0.5x1 minus 0.2x2 is greater than 10, right? So, and the other one is 0.3x1 plus 0.8x2 is greater than 20. Okay, sorry, yeah. So what happens when you add these two? Can somebody tell me what's the result of adding these? Am I audible?
0.8x1 plus
Right.
0.6x2 is greater than equal to 30.
0.6x2 is greater than or equal to 30. Right. So now, so this is what you get from doing this operation. And now the original objective was 2x1 plus 3x2, right? So how does this compare against this 0.8x1 plus 0.6x2? Can you tell me? So if you take this number and this, which is greater?
The left one.
The left one, right? Because you have each of these, the coefficient of x1 you take, it's greater than the coefficient of x1 on this side, and again coefficient of x2 here is greater than the coefficient of x2 here. So immediately you see that this 30, by multiplying this with 0.1, I mean this 30 is a lower bound. Okay, so now what is the best you can do? How far can you go? Now we multiply with 0.1 and that's what we got as the right hand side. Okay, so how much can you go to? Okay, so the idea is, if you multiply with some number y1 and some y2 here, you want to ensure that this these coefficients, so exactly how you got this 0.8 was 5y1 plus 3y2, right? So you multiplied this with y1, you multiplied this with y2, and then you summed it up. So the coefficient you had of this x1 here was just 5y1 plus 3y2. And you had that this was less than 2. Okay, so these two, if you compare these two. Now similarly, you had minus 2y1 plus 8y2, that was less than or equal to 3. Okay, and right, is this clear? It's
Yes,
just,
ma'am.
I'm just generalizing this operation. Okay, so this is what you had, and so the bound that you had, this 30 here, that was just this, right? 10y1 plus 20y2. Okay, so now what you
100 by 1 plus 200 by 2.
200 by 2, right, thanks. So this is 100 by 1 and 200 by 2. Okay, so now what we are trying to do is, you want these to be maintained so that you are guaranteed to have a lower bound, and you want this number here to be maximized. Okay, so then you get what is called the dual problem, so which is, you want to maximize this term 100y1 plus 200y2. So that's what's the best you can do. Okay, so maximize 100y1 plus 200y2 subject to 5y1 plus 3y2 less than or equal to 2, and minus 2y1 plus 8y2 is less than or equal to 3. Okay, and so note that these inequalities will hold only if you multiply this with a positive number, right? Because otherwise the sign of the inequality is going to change. So you want also y1 to be greater than 0 and y2 to be greater than 0. Okay, so you see, this is a new linear program that we have here, and this is called the dual. So this is called the dual linear program. Okay. Uh, yeah. Okay, so I hope this is clear. Are there any questions on this? What we just did? Yes, no? Is it okay? You can type in the chat box. It's clear? Okay. Okay. Cool. So, yeah, so this is this concept of duality that we have. I mean, it's a traditional concept that was there, and so you can, define this for various other forms. The key idea is, try to get a best lower bound for the problem if it's a minimization problem. Okay, so now suppose we have a maximization problem. Okay, so then what we are interested in is finding an upper bound. Okay, so the function, like in general, it's some function that you want to maximize, and what is the best upper bound? So an upper bound would be something like this. This would be the value. So what is the best value? How closer is it to the original problem? Okay, so in this case, you see, like if we try to use the similar idea here, so what we would have is, again, you can multiply this with say some value. Let me say something like 100. Okay, and suppose here I multiplied it with again, say 50. Okay, so now what I'm going to get is when I multiply these two inequalities and add, can you tell me what you get? In the similar manner we did here.
600x1.
600x1. Yes.
950 plus 950x2.
950x2, and that is less than
Equal to 850.
850. Okay, and of course here this was here 9x1 plus x2, and that clearly satisfies that this less than or equal to, right? 9 and 600, and here you have 1 and 950. Okay, so here by similar logic, so what you will do is you will, I mean, to generalize this idea, you will multiply this with some y1 and some y2 here. Okay, and so this side becomes 6y1 plus 5y2, right? And in terms of so this is what you want to maximize. This is the new bound that you're going to get. And in terms of the constraints, what is it going to be? How would you get these numbers? 9 is anyway here, and this is 600, right? So how would you get that?
5y1 plus 2y2 is greater than equal to 9.
Plus 2y2, right, is greater than or equal to 9. Yes.
8y1 plus 3y2 is greater than equal to 1.
2 is greater than equal to 1. And here also you need y1 greater than 0, y2 greater than 0.
Yes, ma'am.
Okay, so this is the dual for this linear program. Okay, so sorry, this has to be now my min, right? Because this is an upper bound and you're trying to find the lowest possible upper bound. Okay, so that's where this becomes min. Okay, so does this make sense to all of you?
Yes, ma'am.
Yes.
Ma'am,
Okay.
I have a question.
Yes, Devyani.
Ma'am, so we're just converting it to a different form. How is that helpful in the end? We just have to solve an LP anyways.
Yeah, so I will come to that. So, of course, the dual has some other interpretations. It's, of course, a different problem that, again, I mean, it's not helping in terms of the complexity in these cases, but you will see, like, there'll be some other interpretations that it's a different problem altogether. Okay, so we'll come to that. Okay.
Okay, ma'am. Ma'am, and also we're just going to use this to find the best, the tightest bound, either upper or lower, not exactly the solution of LP.
Yes, this is just going to give you a bound for the problem.
Thank you,
Okay.
ma'am.
Okay, so yeah, so now if you want to generalize this, so in general, what did we have? We had a linear program of this form, min C transpose X, and you had a set of M inequalities. Okay, so this is what we'll refer to as the primal problem. So this is called the primal, as this is the problem which we originally started off with. Okay, and if you wanted to write the dual, what you did was you multiplied the right hand sides with y's, so you got this. Okay, so because these were inequalities, you just took y's greater than or equal to 0, so that this is maintained. And what you did was, I'm just generalizing it here. Okay, for a general linear program, what you're going to get is, again, you just take the multipliers and sum them up, and you enforce that each of these coefficients have a value, like term wise. In coefficients of x1 will be less than c1, coefficients of x2 is less than c2, and so on. Okay, so now this y1 a1 transpose, okay, so that actually it's just a transpose y. Okay, uh, right, so y1 a1 transpose plus y2, so sorry, this is just x here. Okay, um, it's not x1, x2, and all that. So y1 a1 transpose, y2 a2 transpose, and so on up to ym am transpose. And from this, you're taking the coefficient of x1, okay, the first one. So in short, what you're doing is you're taking this vector y transpose a, okay, and then you're looking at each of the components, and you want to ensure that that is less than c. Okay, so in the general form, what you would write is this b1 y1 plus bm ym, that is just b transpose y. And these constraints that you wrote, it's just a transpose y is less than or equal to c. Okay, and y is greater than or equal to 0. Okay, so this is how you'd represent the dual form. Okay, so go back and try to work this out. Convince yourself that this what you're going to get here is indeed a transpose y. You can try it for these examples as well. Okay, so this is the dual form, and you can also write it for other forms. Like for example, if you don't have x greater than or equal to 0. Okay, so suppose you don't have that. Okay, now what you want is, by the same logic, you wanted something like b transpose y. You wanted to multiply both sides by y, so you'll get y transpose b is less than or equal to y transpose ax. If you remember, this is what we actually wanted. Okay, but now the issue is that, so again here you want to multiply with y's which are greater than 0, so that this is maintained. Okay, but on this side, right, so a transpose y, okay, less than or equal to c, so that inequality, so the two parts to this, right, so you ax greater than or equal to b, that's given to you. So from this you want y's to be greater than 0, so that this is maintained. Now in this side, this will be maintained if a transpose y is less than c, okay, and x greater than or equal to 0. Okay, but now you don't have x greater than or equal to 0 from the original problem. So then what your best bet is to make this equal to. Okay, so that's only the case when you can ensure that this kind of a relation happens, that kind of a relation holds true. Okay, so yeah, because if x becomes negative, then this sign is going to just change, and it is not, you may not get a lower bound anymore. Okay, so then the dual becomes what? Can somebody tell me what the dual is going to be? The same ideas as before, but we are trying to ensure that this is a lower bound. So it's a minimization problem, and you want a lower bound. Okay, and subject to some constraints. So can you tell me what the dual would look like here?
For the A transpose Y equal to C case.
Yes. So yeah, this is going to be a constraint. Okay, so this is the primal that I'm considering. Okay, so maybe let me just tell you. So by the same logic that we had earlier, this is the kind of relation we want to hold. Okay, so if you want this to hold and you want the best lower bound, so the lower bound is this, and what you can do is you maximize this value, right? Because this is the lower bound. And these y's, those y's are the new variables. Okay, and you want to ensure that this is true. Only if this A transpose Y equals C happens, uh, will you get this to be true, this side. Okay, and of course y should be greater than or equal to 0 because you want this inequality to be true. Okay, so the dual becomes of this form. Okay, so remember, like earlier we had a dual composed of all inequalities. So in this case now, the dual is going to have just equalities here. Okay, so A transpose Y equal to C and Y greater than or equal to 0. Okay, does this make sense? Like why we took it in this manner and not A
Yeah, please.
transpose Y less than C? Yeah. So so I mean I'm going over this in slightly more detail because the usual way that people talk of primal dual is it's like it's given as a table, like if you have less than or equal to, then the variable is greater than 0, or they just mug it up. So I didn't feel that it makes much sense to mug it up, so that's why I'll go over this. Okay, so here the problem is minimize C transpose X and AX greater than or equal to B. So X is unrestricted here. So X can take positive or negative values. Okay, so now a lower bound here by going with the same way is if you multiply, we're trying to get a lower bound by multiplying each of these inequalities with some y's. Okay, and so since we want this relation to be true, so when you multiply this with the y's, what you're going to get on the right hand side is y transpose b. For these constraints alone, you're multiplying with the y's. Okay, so y transpose b you got, and the left hand side here becomes y transpose ax. Okay, this part is clear, right? And this is greater than or equal to 0 provided the y's are greater than 0, right? Is this clear so far? It's okay.
Yes, ma'am.
Okay, so so that's about this side. So this side is okay. Now you also want that term wise each of these is less than C. So ideally you want A transpose Y to be less than or equal to C. Okay, so just each of these term by term coefficients you want it to be less than or equal to C. So now this is fine provided the x's are greater than 0. Okay, so if x's are greater than 0, then if you ensure this to be true, okay, then it's fine. You will this A transpose Y less than or equal to C will in effect ensure that B transpose Y is less than C transpose X. Okay, because this side is taken care of. Now if you have if X is greater than 0, this is what will work. Okay, but now since X is not greater than 0, if you had a negative value of X, so suppose X1 is something like -5, then if you take if you multiply this with X1, right? So you take that particular coefficient C1 and A transpose Y, the first component of that. If you compare those two and if you multiply C1 X1 and A transpose Y, the first component of that, times X1, and let X1 be -5. Okay, so this side was true. So so what you had was C1 was greater than or equal to A transpose Y of the first component. But now if you multiply it with X1, the sign is going to flip. Okay, this inequality is going to just flip. So you will get C1 X1 is going to be less than A transpose Y1 and X1 times X1. Okay, so this thing is going to get violated. You're going to have a case where one of the coefficients is going to be less than the, I mean, it's going, you're not going to have this lower bound. Okay, it's not guaranteed that you will have this lower bound. Okay, so that's why when you have X is greater than, I mean, when X is unrestricted, what you can do is instead you set A transpose Y equal to C. So if you set A transpose Y equal to C, now irrespective of the value of X, so if you multiply X transpose A transpose Y, you're going to get X transpose C. Okay, let me just write it as the other way. So if you take Y transpose A transpose X, you're going to get C transpose X. Okay, so and of course you have that Y transpose A transpose X is greater than or equal to Y transpose B from this part. So then this will continue to be a lower bound, okay, for C transpose X. So that's the reason why you make this as an equality. Okay, so does this make sense?
Yes, ma'am.
Yes. Okay. So I want to hear from the others too. We just type or
Ma'am,
say yes.
A transpose Y is still a vector, and when we are comparing it with C is also a vector. So how are we checking the inequality? Is it component wise, or like we are taking a norm?
So these are all numbers, right? C transpose X and B transpose Y. These are all just numbers, right? Like in
Yes,
this
ma'am, but
example.
when we were comparing A transpose Y with C. So what we were saying is A transpose Y should be less than equal to C.
So okay, yeah. So C is a vector, and A transpose Y is also a vector, right? Because A was what Rm cross N.
Yes,
Okay,
ma'am.
M and Y was what Rm, right? So this is a vector with n components, and this is also vector with n components. So you're taking like term by term. So component by component comparison. It's not a norm.
Okay, ma'am.
Okay. Yeah, that's a good point. So like how we did with these examples, we took each of the components, like each of the coefficients, right? So this was exactly the A transpose Y, right? So this part. Okay, so what we did is we took point 0.8. Okay, so that is the first component of A transpose Y. 0.6 is the second component of A transpose Y. Okay, so yeah, the first component becomes this, second component becomes this. So that's the idea. Okay, so yeah, are there any more questions on this? You're quiet, so I need to hear some response. What's going on? Is it clear? It's not clear?
Clear, ma'am.
Clear? Okay. So somebody else, Manan?
Yes, ma'am. No questions.
No questions. Okay. Okay, Bhavna is clear. Thanks. Okay, so that's the sort of way you write the dual. So, I mean, you should try different combinations of this. Okay, so suppose you have like a maximization form and you have x unrestricted. So how would you write the dual? I mean, the concept is the same as what we saw. We saw an example for maximization also here. So it's you have to extrapolate it for the general case. Okay, so you should try writing out the dual forms for various combinations. So you take maximization, you take x unrestricted, or the other cases you can take equalities. So now instead of you can have minimize C transpose X Ax equal to B, right? So there, what will change? Okay, so those are some things you can derive all of them using this same idea that I've told you here. Okay, so you should go and you should surely try to write these out. So I don't believe in mugging things up from a table. So that's why I think it makes more sense to once you have this idea clear, you can immediately work it out yourself and get it. Okay, so some textbooks would also have a different approach to writing the dual. So they write it in terms of what's called the Lagrangian. Okay, so the Lagrangian duality is something which it is useful, and it's definitely more useful in general constrained optimization. But for linear programs, you don't have to go all the way to a Lagrangian. Okay, so we will do a Lagrangian at a later point. Maybe after the linear programs, we will come to that. But what I want you to get is, you can derive an LP dual with these simple ideas that we discussed. Okay, so that should be good enough to get a dual. So now let's just see some examples in practice. Okay, so, and like Devyani was asking, what is the use of it, or what can we do with it? Okay, so it turns out that many times these duals have different kind of interpretations. Okay, so for example, let's see this diet problem that we first talked of, when I introduced you to linear programs. So the problem is this: there are some products, okay, some food products that you as a buyer you want to purchase. So something like what we talked of was these quantities, I mean these excise that could correspond to maybe rice, dal, okay, and maybe some vegetables, okay, something of this form. Okay, so these are the products, the food products, and they all have some nutritional value. Okay, so you want to see how much quantity of each of these products you want to purchase so that you meet your daily requirement. Okay, so the nutrients could be something like we saw this earlier, like carbs, proteins, okay, and maybe some vitamins or whatever. Okay, so the you want to also meet your daily requirements, so that is the quantity, that is bj, that your body requires. Okay, and if you buy a some unit of product I, 1 unit of product I, the cost incurred is ci. Okay, and so you want to minimize the summation ci xi, the total cost you want to minimize, such that you are also able to meet your daily requirement. So that gets captured using this ax greater than or equal to b. So in particular, AJI is the amount of nutrient I. Okay, so let's just write this in a little more detail. So what we have is minimize C1 X1 plus, let's just take three food products, C2 X2 plus C3 X3. So maybe this is like rice, and this is like dal, and this is some veggies. Okay, and you also know that for proteins, okay, so you have each each unit of dal has this much protein, so something of that sort. Okay, so let's say like A11 of X1. Okay, so this is the say amount of carbs in 1 unit of rice. Okay, now amount of carbs in 1 unit of dal, that is A12. Okay, and similarly amount of carbs in 1 unit of vegetables, so that is A13 X3. Okay, so this is the total quantity of carbs you're going to get. Okay, if you have this x1 x2 x3, if you purchase x1 x2 x3 amount of each of these food products, and you want that to be greater than b1, so b1 is the daily requirement of carbs. Okay, so similarly you want A21 X1. So this is for the proteins, say. So A21 X1 plus A22 X2 plus A23 X3. So this is greater than or equal to B2. Okay, and yeah, similarly you can go on. Okay, so and you also want X1, X2, X3 to be greater than or equal to 0. Okay, so this is the primal form. So this is the diet problem. And now if you write the dual, okay, so the dual of this using the same way that we did earlier. So let's just say that the multipliers are y1, y2, and so on. So let us say there are let's just say there are 3 products. So let's keep it simple. So here there's one more y3. Okay, so what, let me just write this, A31 X1 plus A32 X2 plus A33 X3. Okay, so now what you're going to get is the dual is just going to be max B1 Y1 plus B2 Y2 plus B3 Y3. Okay, subject to you take these coefficients. So A11 Y1. So A11 Y1 plus A21 Y2, you're multiplying the second one with Y2, and A31 Y3. So those are the, if you sum those up, you get the coefficients of X1. Okay, so A21 Y2 plus A31 Y3, that is going to be, it needs to be less than C1, right? So in that similar manner, you can write all the costs. So in general, you will get something like, what do you get? I mean, it's A transpose Y less than C, right? So yeah, I mean, you can work it out. But so if you look at this problem, so again, you also want Y1, Y2, Y3 to be greater than or equal to 0. Okay, so so if you look at this, there is some interpretation here for this problem. So namely, so what the primal had a viewpoint from the customer's side. Okay, so now suppose if instead of okay, there's this thing where there's a shop where you have these products which are being sold. Now instead of that, suppose you are going to like maybe you own some company where you're going to put in pills. You're going to introduce some kind of pills which have all these nutrients. Okay, and what are the prices that you want to charge for each of these pills? So there is one pill for carbs, there's one pill for proteins, and there's one pill for say what's that thing, vitamins, and so on. Okay, so what is the prices that you want to charge for each of these pills? So that is the interpretation that the dual has. So let's just see why that is the case. So in terms of B1, B2, B3, so those are, if you remember, that's the quantity of the nutrients that the body requires. So if somebody is going to buy these pills instead, what they will buy is B1 quantity of these pills, B2 of these pills, and B3 of these pills, and so on. Okay, so the total revenue that you will get from introducing these pills would be this term, B1Y1 plus B2Y2 plus B3Y3. Okay, now if you're going to introduce these pills, when will somebody choose to go for these pills instead of these food products? From the customer's point of view, they're trying to minimize their cost. Okay, so if they end up paying more in the process of taking these pills, then they're not going to buy these pills. Okay, so these constraints sort of ensure that. So in terms of food product one, okay, so you would spend C1 as a cost. Okay, and so this A1Y1, the price that you spend, okay, in terms of getting these, whatever you would have got from this food product one, okay, the all the nutrients that you would have got, okay, and the price that you're instead spending there, that is A11Y1 plus A21Y2 plus A31Y3. Okay, so that is the cost that you're spending effectively. Okay, instead of you go for pills than food product one, this is the cost that you would spend. So so you want that to be less than C1. Otherwise, people will say like, okay, let's just buy the food products. These pills are too expensive. Okay, so in that way, you want this to hold for every other food product as well. Okay, so that is the interpretation the dual has. So it's in terms of the prices of each of these nutrients, or in general, it's the price that you want to pay for these constraints, for meeting these constraints. Okay, so I hope this interpretation sort of makes sense. Okay, so please ask if something is unclear. Okay, right. Guys, is it clear? Yes, no, it's clear. Okay. Okay, so yeah, you can complete this dual form as well and see what see what that you get the same interpretation for the other constraints. Now, another example I want to take is the transportation problem, which we saw again in the first class. So here, what we saw was there were several sources. Like you wanted to ship some products from several origin locations, and you want to ship them from the origins to the destinations. Okay, so maybe like different cities or even different factories within the same city or whatever. Okay, so there's a cost for sending some goods from location I to J, and that cost is given by Cij. Okay, and from the source side, so these are all the origins. Okay, so there are many origins and there are many destinations. Okay, and there's a cost of sending items from here, from origin to the destination, and at the origin, these you can think of as the factories where these items are produced, and there's a limit of AI. Okay, so A1 for the first origin and A2 for the second origin, and so on. So you can produce up to A1. You can send some A1 items from the first origin, and in the destination there's a demand of B1. Okay, so B1, B2, and so on. So these are the demand at the destination, the demand values at the destinations. Okay, so you want to ensure that you send items so that all these demands are met. Okay, and you don't want to produce more quantity also at the origins, so you want to ensure that you exactly send AI amount. Okay, so these are the sort of constraints. Okay, so xij is how much you send from I to j. Okay, and the sum over all these j's, that should be exactly equal to ai, and the sum of xij's over all the i's. For each j, for each destination you take, the sum of all the incoming quantity, that has to be bj. Okay, because that's the demand. Okay, and you want the cost to be minimized. So this is one example we saw, and this is the, it's called the transportation problem. Now here, if you write the dual, okay, so here remember this is an equality form. Okay, so let's say like we multiply this with ui, and these are multiplied with vj. Okay, so now what you have is the bound is going to be ai ui plus summation bj vj, right? So for all the destination pairs and all the source pairs. So I'm just taking the right hand side here. Okay, so this is a quantity, so this is a minimization form, so you want this to be a lower bound. Okay, and you want the best lower bound, so that's why you're trying to maximize this. Okay, so remember this has the form minimize C transpose X such that AX equals B. Okay, so it's of this form. Okay, so now if you write the dual of this, you're going to get what? So B transpose Y, so you have max B transpose Y subject to, so this side it should hold, right? So B transpose Y you have, and that's equal to Y transpose AX. And you want this to be a lower bound for C transpose X. And here X's are already given to be greater than or equal to 0. So you can have A transpose Y as less than or equal to C, that's okay. But here AX equal to B, I mean, that's, you don't need any constraints on Y's, because that is satisfied even, I mean, this part is going to be satisfied even if Y is positive or negative. So there's no constraint on Y, so this becomes the dual. Okay, so I hope this is clear, like how I wrote the dual for this problem. Okay, so I'm just going to substitute this here. So maximize summation ai ui plus summation bj vj's such that now it's these constraints, right? So you take for each xij, you take the coefficients. If you do this multiplication of each of these with ui and these with vj, and then you take the coefficients corresponding to each xij. Okay, so for every ij pair, you will have one constraint, right? So xij, if you take the coefficients, you will, what will you get? So fix an I and j. So what are you going to get when you multiply these with ui and vj's, and when you sum them, what's going to be the coefficient of xij? Okay, you're all very quiet. That's not good. This is not clear as what's going on. Can someone tell me? Okay, I have to start asking people now. So Siddharth, what's going on? Okay, Siddharth Solanki.
Ma'am, I like sort of couldn't get this formulation.
Which one? This part, the writing the dual for this?
Yes, ma'am. Yes, ma'am.
This one. Okay, so let me just explain this. Let's not go into the transportation part yet. Okay, so I'm just doing the same, and you understood the previous steps, like for the previous linear programs, how the dual was written. Did you
Yes, ma'am.
understand that?
I
That
got
is
it.
clear, right? So I'm just trying to use the same idea. Like here, there's just a small difference that here we have this ax equal to b form. Okay, so in the earlier problems we had inequalities, and here we are having an equality. Okay, so I mean some things will change when you write the dual. Okay, so so to start off with, what we did earlier was you multiplied everything with y. All the constraints you multiplied them with y. So b is a vector, and you multiplied each of these constraints with y. So y1, y2, and so on. Okay, and what you got in the process was this b transpose y. Okay, so you're just summing, you multiplied each of them with y and you added all these resulting constraints. So what you got was b transpose y equals y transpose ax. Is this part clear? Up to here it's okay?
Yes, ma'am.
This is clear, right? Okay, so that part was clear, and you want this b transpose y to be a lower bound. You're minimizing a function and you want a lower bound. Okay, and so you want b transpose y to be less than or equal to c transpose x. Okay, and there is this intermediate thing that is helping you to get this point. Okay, to achieve this, so you actually want y transpose ax to be again less than or equal to c transpose x. Okay, so so to do that, now you already it's given to you that x is greater than or equal to 0. Okay, so each component of x, so each of the vectors and each of the components x1 to xn, those are all greater than or equal to 0. So now A transpose by this is a vector, and if you take each of the coefficients, if you take x1, you take its coefficient, you're going to get some A transpose by the first component of that. If you make that less than or equal to C1, then you're done. And you keep doing this for every component of x. Okay, so you can so it's just enough to make this as A transpose y less than or equal to c. So if you make A transpose y less than or equal to c, then you will get this side. Okay, because you know that x's are all greater than or equal to 0. Okay, so that's why these constraints come in. Okay, so like if you just don't put in any constraints, what are you going to get? You're just going to get b transpose y, and that's just going to be some upper bound. I mean, some bound it is. Okay, so you don't know what. It's just going to, if it's an unconstrained problem, it's just going to be unbounded. So that's why you need some constraints on these y's. Okay, and the constraints are such that it helps you achieve this as a this b transpose y is indeed a lower bound for c transpose x. So this is kind of an intermediate handle that you have to ensure that this is indeed happening. Okay,
I mean, the
so
previous problem, I could see that when we are multiplying y, how the A transpose y should it be less than c? But in this one, uh, like it doesn't follow from the constraint that A transpose y, why should it be less than c? Like, transpose.
okay, so let's take something. So what? Let's take if it was not less than or equal to c, right? So suppose um, what you suggest something, right? Like what do you think? What was an alternative that you could have?
I just can't see the like what's the relation between C transpose X and A transpose X, because like that's just a constraint which is not forcing anything.
So this constraint, right? This A transpose y less than or equal to c, that is going to ensure that this is true, right? Y transpose Ax is less than or equal to c transpose x. Do you agree with that?
Yes, ma'am.
Right, and because you have this b transpose y in turn is equal to A transpose, I mean, this y transpose Ax, because you already have this is true, right? So then in turn it's ensuring that your b transpose y, which is your bound, that is indeed lower than c transpose x, right? um, I don't know if that
But B transpose Y wasn't our bound. Like we wanted to minimize C transpose X. So like I can't see the relation in this problem with
no,
the
no. So, right. So, this is the original problem. You're right. So, minimize C transpose X such that AX equals to D. This is the problem with which we started off. Okay. Now, what we are saying is we want a lower bound for this problem. So, so this was some function C transpose X, and there's some optimum value of it in this feasible set. This was something. This was the optimal value. But what is a lower bound for this? Okay, so the dual is about finding some lower bound here, some value which is less than even this optimum. And okay, so it's, yeah, so we are precisely trying to construct lower bounds for the problem. Okay, and in that we also want to see what's the best lower bound you can consider. What is the max? If you, I mean, is the lower bound? I mean, if you say that this is a lower bound, okay, can I have a better lower bound? And in short, like, what is the best? The best lower bound is of course going to be exactly the same value, right? Something which meets it. Okay, but is there, how can you get other lower bounds for this problem? Right, so the whole idea is to get some lower bounds if it's a minimization problem, and if it's a maximization problem, what is an upper bound? So it's in sort of you're trying to say that you will not go below this. So if this is a lower bound, so this is a lower bound for the problem, the optimum value by solving this original optimization problem, you are guaranteed that you will be at least as good as L. Okay, your optimum value is not going to go below L. So you're trying to get that kind of a guarantee, right?
Yes, ma'am.
So that's clear. Okay, so then so that's the whole objective, right? Try to what's the best lower value you can get, not how far can it go till. Okay, so that's the reason why you want this relation. You just want a lower bound, so B transpose Y. So that's the lower bound that we are proposing, and you want that to be less than C transpose X. End of the day. Okay, this is what you want, but you can't just take any Y, right? I mean, you have to have some constraints. Otherwise, any Y, if you allow this Y to be free, it's just going to be unbounded. I mean, if you get a bound like negative infinity, okay, that is not a useful bound for you. So you want to put in some more constraints so that you will have this. I mean, at best, how best can you get this? And that's why you have these kind of constraints, which will ensure more information on why you give that helps you to meet your lower bound. Okay, so that's the reason why we have these constraints. Okay, so I don't know, I think I'm running out of time. So maybe we'll come back to this transportation problem again with the interpretations and things. I mean, there's a lot more. I mean, more things that the dual buys you. So we will see this maybe in the next class. Okay, so I will hang back if there are any questions. So if not, so thanks for being here in the morning. So we'll see you on Thursday.
Thank you, ma'am.